Hello, good day, Dr. Khan. Today, our team will be making a presentation on the optimal battery charge and discharge technique for electric vehicles in grid integration. This presentation is presented by Daniel and Endurance as part of this course requirement. So we're going to focus on some major aspects of this project. So we're going to talk about the introduction, the active rectifier. We're going to elaborate on the buck converter as well as the control for the system. The active rectifier is very important in this project because it is needed to overcome the shortcomings of the normal rectifier with diodes. The normal rectifier draws sinusoidal current. This can also cause more harmonics as well as it reduces power factor because of the high voltage drop, and as such the active rectifier can do better in this regard. Also, in the active rectifier circuit, our inductor is connected in the series with the AC voltage source, and the diode in the normal rectifier circuit are replaced with either the MOSFET or the insulated gate bipolar transistor. When we talk about the buck converter configuration, this comprises mainly of switching semiconductor devices such as the MOSFET and the insulated gate bipolar transistor. The buck converter configuration uses a pulse width modulation to alternatively connect and disconnect the input voltage from the rest of the circuit through either the IGBT or through the MOSFETs, which are the two major switching devices here. An inductor is placed in series with the switch and store energy in the form of magnetic field when the switch is closed. Also, a diode is connected in parallel with the inductor to allow current to flow only one direction in. This is to prevent the backflow of current when the switch is open. And lastly, the capacitor often placed at the output to smooth out the voltage, and with this we mean you're trying to remove those ripples so we can have a smooth voltage in the system.
So for the operation of the buck converter, how it works in this system, it is used for the charging mode, and then in the discharge mode we use the boost converter. So in the charging mode, the buck converter sets, so we have the output voltage and the current. So let's say we have an output voltage of 24 volts, and then we have a set point or a set voltage of 16 volts. This the control of the buck converter is able to sense the output voltage, which in this case I give an example to be 24 volts, and then compare it to the 16 volts reference, and then it now enters into the PI controller for the adjustment to be made to the width of the pulses to be sent to the gates of the MOSFET. This is able to control the voltage at the output, and then in that process this is used to charge the battery. So let's move on to the overall system, which comprises of the charging and then discharging. So let's assume we are taking power from the grid to charge our battery. We have our AC source coming in, and then this AC source is being connected to an LCL filter, which is able to reduce or remove unwanted signals, and then also reduce third harmonic distortion from our system. This is then connected to the active rectifier. For the active rectifier, it's mainly comprises of IGBTs, 4 IGBTs, because this one we are doing single phase. So 4 IGBTs which turns on and off per two, like two pairs. So in this example, the IGBT with PWM1 and then PWM4 turns on in one cycle, as PWM2 and then PWM3 will stay off. So in the next cycle, the PWM3 and then PWM2 will stay on or will come on, and then the PWM1 and then PWM4 will go off. So after the switching, now we get a pulsating DC, which is not smooth for our operation. So we have our DC link over here, in the middle of the circuit to smoothen or to remove ripples from the DC and give us a very straight signal. This signal becomes our main DC, and then this one is used to charge the battery. So for the charging, we have the back using a MOSFET, and then this MOSFET is connected to an inductor and then the capacitor, and then it is able to charge our battery. So for the charging operation, there is a little bit of controls which we will delve into further to see how it does the control to charge the battery. But in the discharge mode, it uses the boost converter, and then it moves on to the active rectifier, which does the switching and all that to convert it back. So yeah, the next slide we will delve into the controls deeper. Now let's go deep into the control system for the overall project. This project we use the PR and the PI controllers for voltage and current sensing of the battery charging and then discharging system. So one of the voltages we controlled was the DC link voltage. We set it up at 400 volts, and also so based on whatever you get at the DC link, that voltage is being compared to this 400 volts, and then the difference is then fed into a PI controller, which is a proportional integral controller. This output, the output from the PI controller, was then multiplied by cos omega t to get our current reference, and then this current reference was compared to the inverse current from the inductor. So this inverse current is basically the reverse current that flows when there is a sudden interruption of the system, and then the difference between the current reference and then the inverse reference was then sent to a PR controller. The PR controller is the proportional resonant controller, and it is more capable of efficiently handling resonant load or load that can change very frequently. So based on this one, the width of the pulse width modulation that goes to the gate of the IGBTs used for the active rectifier changes or modifies to suit the output, what you are getting from the output, and then the desired voltage being set as the reference. Yeah, and we also have the PLL block, which is the phase locked loop block. This one is used to synchronize the frequency and phase of the input and output signals. It's something we use in our control system. And then we also have our control battery current control. So for that one, we set the voltage of we set the current of the battery at 12, and then we compare that one to whatever we are getting at the output of the battery. So the difference was sent to a PI controller, and then this PI controller corrects the error, and then based on that it is able to regulate or modify the width of the PWM pulse signals going to the MOSFET of the IGBT of the MOSFET going to the MOSFETs of the back converter and then the boost converter based on either charging or discharging. Okay, on the left side of the slide is the control DC link voltage. As I said, we set the control DC link voltage at 400 volts. So based on whatever we get at the output, we compare that one to the set point or the reference, which was 400 volts, and then our controller was able to control and then maintain it. Although we have a little bit overshoot, which isn't too much, and our settling time is about 0.5 seconds, which is really good. So, and also from the graph on the right, it shows that we have a unity power factor, which basically means our voltage signal and then the current signal, they were in phase. So this is one main reason why. So this one was taken from the input side, and this one makes the active rectifier a very reliable option to go in for, because even when you go for diode rectifiers, there are a lot of voltage drop across the diode, so you have a lot of losses. But for this one, you don't have any loss. You also don't have any issue related to commutation. Okay, so on the graph on my top left is the battery charging control signal. So the current signal was, as I said in the detailed control system for the overall project, the current signal was set at 12 amps. So our system was able to regulate the PWM signals to make sure that the output current is always 12 volts. And then below that graph is the control signal. So this is the control signal for the battery charging. And then on the right side, we have the battery in discharge mode. So when the battery is discharging into the grid to be used by our homes, commercial use and all that. Yeah, this is the graph that shows, and then it makes use of the boost converter rather than the back converter in discharging the battery. Here are some references used in completion of this project. Once again, this has been a wonderful presentation on optimal battery charge discharge technique for electric vehicles in grid integration. Thank you.